I'm Nidhi Veerendra, and I'm thrilled to share my project, NeuroAid, an AI-driven bioinformatics tool for early screening of behavioral challenges in children. As a student deeply passionate in neuroscience and data science, I designed this project to ask, can EEG signals and artificial intelligence be used to detect early signs of conditions like ADHD before school age? If the answer is yes, that could open doors to earlier support and change the trajectory for so many families. Let's find out. Many behavioral conditions like ADHD are diagnosed way too late, often not until age 7 or older. But the signs often appear way earlier: difficulty focusing, impulsivity, and social challenges. That lag leaves families in a limbo, schools unprepared, and children without early intervention. As I learned more, I started wondering, can we use brain waves to give us a heads up? EEG, which captures electrical activity in the brain, might hold subtle signals of neurodevelopmental differences. Using bioinformatics, I wanted to extract those signals and build a machine learning model that could help not to diagnose but to flag patterns worth investigating. For this, I used a 2024 EEG dataset from Figshare containing data from 88 children, half diagnosed with ADHD, half neurotypical. Each child's EEG was recorded across 18 electrodes placed at different regions of the scalp. My research question was, can a machine learning model distinguish ADHD from control cases based on which EEG features alone? And if so, which regions of the brain were most predictive? Before training any model, I visualized EEG signal distributions using kernel density plots. Right away, I noticed separation between ADHD and control groups in frontal and central regions, specifically in channels like FP1, F3, and C3. This was my first clue that these signals weren't just noise. They carried meaning. It also aligned with existing neuroscience, since ADHD is often known to affect the frontal lobe's role in executive function and impulse control. So I chose the YBS model, which is a gradient boosting algorithm known for handling high-dimensional data with speed and accuracy. I split the dataset 80-20 for training and testing and used random oversampler to address class imbalance. My evaluation metrics included ROC, AUC, accuracy, and the confusion matrix, ensuring both interpretability and statistical rigor. YBS also let me inspect features' importances, which was critical to answering my second question: which brain regions matter most? The final model received 76% accuracy and an ROC-AUC of 0.84, which shows strong discriminatory power. The most important features were CZ, P3, FP2, and F4, spanning the frontal and parietal lobes. These are the very regions associated with attention, emotional regulation, and working memory. So the model wasn't just performing well, it was learning in ways that reflected human biology. I also applied principal component analysis to visualize the high-dimensional EEG data in 2 dimensions. The PCA plot revealed noticeable class separation, meaning that even when reduced to just 2 components, ADHD and control cases still follow different patterns. And the ROC curve, with an AUC of 0.84, confirmed that the model wasn't just memorizing, it was generalizing. That was a pivotal finding for me. It meant EEG-based screening had real measurable promise. So, I wanted to dive deeper into how brain activity varied across groups. So I created box plots for each EEG channel and found that children with ADHD had more variability and more outliers, especially in the frontal lobe. I also plotted a radar chart comparing EEG values between classes. It revealed consistently elevated signals in the ADHD group across multiple channels. Together, these visualizations added biological texture to what the model was seeing and giving, which gave me a deeper understanding of the underlying patterns. Exciting this is, I'm also aware of its limits. NeuroAid is not a diagnostic tool. It's a support system. It should be used to prompt earlier conversations, not replace expert evaluation. In the future, I plan to integrate behavioral data like tantrum frequency, sleep cycles, or language delays to give a more complete developmental profile. I also hope to build a clinician-facing interface so therapists can input EEG and behavioral markers and receive tailored risk scores or screening prompts. And the goal is ethical, accessible, and personalized care, guided by data and grounded in empathy. Thank you so much for listening. I'm so grateful for the Youth Bioinformatics Symposium and ISCB for this opportunity.